All right, Newton's laws of motion, quick review, and then working with Newton's laws and the so-called equilibrant force, which I'll explain. So it's on the menu for the day. So here we go, Newton's laws. Might be familiar with some of these, right? Hopefully already, but here we go. So objects remain at rest or in uniform motion in a straight line unless acted on by an external unbalanced force. So really the buzzword for that one is that objects have inertia, right? That's a key concept to know about. Wasn't super easy for humans originally to kind of realize that because of friction and so on, right? So Newton had to do a lot of work to convince people of this. People would naturally have just thought that objects in motion tend to slow down and stop, right? So yeah, that was tricky for Newton to realize and then to convince the masses around the world, right? So, if you want to get something sticky off your fingers, like gum, uh, you can flick your finger and, basically your finger moves and then stops really quick and whatever's stuck to your finger um, uh, continues in that motion that it had. Getting snow off your boots, why does stomping your feet work? When you bring your boot down towards the ground quickly, your boot stops instantly when it hits the floor. The snow doesn't stop instantly because it has inertia, right? Lots of examples you can think of to do with inertia. In grade 11, I showed tons of different demos. Go back to the 3U physics lesson on my channel and check out the lesson on inertia if you don't have a ton of things in your mind as to what inertia can explain. Second law of motion is that when you push on an object, it accelerates, right? So let me undo that massive delete by accident. So you push on an object and it accelerates, right? So basically it's the amount of acceleration is directly proportional to the amount of mass and of course the amount of push, right? So that law is written mathematically as F equals ma, and so basically acceleration is proportional to force, where the proportionality constant is mass, right? A big thing to remember about this for strategy and working through questions is that we have this fundamental link between net force and acceleration. In a question, if you're given the net force and the mass, you can definitely calculate the acceleration, and vice versa. If you're given the acceleration and you know the mass, you can calculate what the net force must be. And so that is often a starting point for questions. You're working through them. So here's a perfect example. You have a force of 10 newtons forward is applied to a 4 kilogram block on a table. There's a frictional force of 2 newtons backwards acting on the block. Let's just calculate the acceleration, right? So the key is, of course, we can figure out the net force first and then determine the acceleration, right? So the analysis and solution to this, we know that net force is all the forces added up, and we know that net force equals ma. So if we put the applied force plus the friction force in as F net, end up with this new version of the things kind of just put together, right? And so then we can put some numbers in, and in the question we had that it was being applied forward and and so on. And so basically we called the forward direction, call forward positive. And so that's why the 10 newtons is forward and then the friction is backwards, right? So and then on the other side we have our ma, which is the mass times the acceleration. So the mass was given as 4 kilograms. So there you go. Combine those things, end up with the 8 Newton net force. And the way this question is shown, that's not as obvious, but I mean, I'll show another way to look at this, but it might have been fairly obvious, right? That's your F net there. And so really we have an F net equals ma. We're dividing both sides by 4. And I usually would show, divide by 4. Make sure everybody can follow the little math steps in the context of a physics class. And so you end up with the acceleration is 2. They have it in newtons per kilogram, which is very odd. Really, it's kilograms meters per second. Sorry, it's just acceleration. Wow, have the kilograms in my mind there. It's just meters per second squared, right? The Newton itself is kilograms meters per second squared. So newtons divided by kilograms is the same as kilograms meters per second squared divided by kilograms, right? Because newtons is MA, right? F equals MA. The M and the A are kilograms. So this is just old stock from the old online course. So little weird things like that I miss correcting sometimes, but you know what? You're going to see that kind of stuff here and there as you go to different resources anyway. So it's good to have lots of different experiences, right? So all good. My preferred kind of way to show this might have been this way instead, where you just say, okay, F net equals, calculate it out, and then put the net force value into the net force equation and calculate it out. It just makes it a little more obvious that you have lots of pieces of information, right? The question could have had a part A, what is determine the net force, and then part B, determine the acceleration if they're able to do that. So it stands out more this way that you have determined the net force. All right. Next up here, this one I'm just going to show quick and point out something that we get here. So we have another block moving along at 15 meters per second forward, the 4 kilogram block, and it's under the influence of friction force only. So it's coasting, and the block comes to a stop in 20 meters while it's traveling and slowing down. And it wants you to calculate the friction force. So assume the force of gravity is canceling out the normal force in the block. In other words, like it's on a flat surface and it's staying that way, right? So gravity, basically they're saying gravity is not a factor. So when they're asking to calculate the friction force, that's the only force that's on the object, right? So in other words, they're asking you for the net force. So you should be noticing, oh, okay, well, if I can calculate the acceleration, then I'll be able to calculate the net force, right? So really your first thing is this. You have to get that acceleration based on the information that's given. And of course, if you look V1, V2, acceleration, delta T and delta D, we have the initial velocity and the final velocity, because it gave us a V1 initial velocity of 15, a final velocity of 0 because it's stopping, and the displacement. Right, so you're going to circle, circle, circle on the uniform acceleration equation selection matrix thing, and pick an equation, right? So absolutely getting that acceleration first, and then continuing to get next here? The friction calculate. I forget what we're even being asked to do here. Calculate the friction force, right? The net force. So the analysis of this, nice little free body diagrams, not a bad idea always. You've got your friction force on it, and they showed these guys canceled out, so you might not even have drawn those because they're irrelevant. But basically you just have that. I wouldn't say that was a critical free body diagram to draw. The biggest thing here, of course, is to select the equation and do the work, get that acceleration, get that net force, right? Get that acceleration, and then that'll get the net force. So we can say then F net equals ma, and so you have the mass and you have the acceleration, so you'll get the net force. Is the idea, the name of the game. And so it looks like this. You have the equation. They say rearrange and solve for the A. Well, that's the option 2 that I talked about before, where you can do the rearranging. If you're doing that, you have to show that though. Like if you're starting with A equals V final square, like it makes me worry that you're thinking that that's an equation you need to memorize and be familiar with, right? So please show the algebra if you're doing that. It also makes me think that maybe you got it from somewhere other than your brain. AI, Google, whatever. If you're starting with an obscure equation that no one ever uses as a starting point, it's a good indicator that you don't actually know what's going on. So yeah, let's not do that. So we get that acceleration, then of course acceleration gives the net force, right? So F net equals the force of friction, and so F net equals ma, and blah, 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 right? So, and you end up getting your friction force being the 22 newtons backwards. And therefore paraphrase and so on, right? Oh, great. Yeah, my preference probably would have been just to plug numbers in, right? We have the 15 and the 0 and the plus 2a delta d, whatever that displacement was 20. and so on, and then just algebra solve for A. Right? How I typically go about it. But if you're going to rearrange for the acceleration or whatever you're solving for with the variables, show the work. And finally, Newton's third law. Newton's third law: for every action force is an equal and opposite reaction force. Yeah, that's the thing, right? In grade 11 in my class in person last semester, we saw something interesting, but this is they're saying this is the so-called horse dilemma. It's not really a horse dilemma, but whatever. It's kind of amusing. I'll leave it. So if a force exerts a horse on a cart, if the force that the horse exerts on the cart is equal in magnitude to the force that the cart exerts back on the horse, but is in the opposite direction, how can the horse possibly pull a cart forward? Isn't the net force zero? Press pause. Think about it. How do these action and reaction forces that are always in opposite directions and the same size not add to zero? So if the horse pulls with 1,000 newtons forward on the cart pulls with 1,000 newtons backwards on the horse, and so we have this plus 1,000 and a minus 1,000. You're picturing hopefully the net force equation where the forces just all add up. Why doesn't it end up being zero? Okay. Well, answer eventually here, if you're hopefully thinking about it first, but the answer is if we consider these like two blocks here, right? And we have like the blue block pushing on the red block, and the red block pushing on the blue block, right? I don't know why they have that there. It's a push, I guess. I shouldn't cross it out, but I mean, really, because of that applied force there, you've got the blue force. So let's go force of blue on red for short forms here. And then we have the force of the reaction force, right? So they've got an action and reaction force. So this, I would say, is the action force. And over here, we've got the force of the red on the blue, and that's the reaction force. And those are supposed to be about the same size. They look about right. I might make that one a tiny bigger or something like that. But yeah, they're the same size and so on, right? And so why don't they cancel out? Right? Well, the answer is because they're not on the same objects, right? How could they possibly cancel out? It's like a force on one side of the room on something and an equal and opposite force on the other side of the room on something, and they're not on the same objects, right? That's the answer to the weird thing. But yeah, so if we separate those out, they're just forces on separate objects. So the way it goes. Alrighty. I was in my first year of teaching when I got asked that question, and I just had never thought about it, and it didn't. I don't know. I had to go home, and I said, I don't know. Just let me think about that, and I'll get back to you. And then I went home and thought about it and looked at it and everything else, and realized, oh my God, they're on different objects. So went back and answered the question the next day. It's all good. So the other thing, that's the Newton's laws. We're looking at that equilibrant force. Equilibrium and equilibrant is the word they use for some reason in physics. It's not even actually a real world word by the sounds of it, anyways. At least in my spell checking, it doesn't recognize it. It is a real word, but spell check doesn't have all of them, I guess. Here we go. Forces on stationary objects and forces with constant velocity. So we can think of it as a static equilibrium where it's just stationary, or in a dynamic equilibrium where it's moving with a constant velocity. Either way, what you're looking at in a situation like that is that the net force is zero, right? No acceleration, so no net force, right? So the key here is there's no acceleration. And so right there, no net force. And that's definitely something to recognize and know, right? That's what I've been saying earlier in the lesson with that little remember thing here. Remember, acceleration and net force go hand in hand, right? So let's look through this. So we say, okay, we've got a net force of zero. Well, we're going to look at what these guys add up to, I guess, right? So we look at the net force. You say, okay, well, there's a net force would be the F1 and F2 added up, and then there's the friction force as well. It wants us to know. Like, it was pretty obvious that we're looking for the friction force, right? So I could even color code that guy to make it obvious that that probably wouldn't have been too easy or too difficult to notice, needed to be on the list, let's say, right? That force there is the force that's balancing everything out. And so that is the one that is called the equilibrant force, right? So that's what we're looking for. So if you plug numbers in, you've got the 0, and then you take away F1 and F2 from both sides, and you end up with the equilibrant force, the friction force, equal to the opposite of F1 plus F2, right? And so adding up F1 and F2 is old news. Do it by components or by trig, sine law, cosine law, or, if you don't have those math skills, you need to learn them. But I mean, humans could get the answer by scale diagrams if they needed to, right? So I'd recommend you go back to, I think it's lesson 4 or 5, right, where I showed that stuff in detail. Review if necessary. Do this as practice. Make sure you can get the right answer consistently, right? So you're looking for 30 newtons west, 16 degrees south, unless I've made an error somewhere. Okay, check it out. Let me know if you need help. Continuing on with the equilibrant force. Picture this scenario here where you're hanging things out to dry. I think the kid got wet. Mom and dad were angry. I don't know, whatever. It's a weird picture. So if you look at this situation, if we add those two tension forces, there's tension forces in this clothesline, right? If you add those two tension forces up, what do they end up adding to? Well, they end up adding to the opposite as the gravity, right? So think of that as I guess that's the addition of the forces, and then the equilibrant in that case is the single force that's balancing those, right? So we got Fg, right? And then we have this result here, equilibrant force. So I don't know what you want to call this, call it F1 plus F2, but equals the opposite of the gravity force, I guess, right? So like that, however you want to word it. Could have been Fg equals the opposite of those two, but yeah, just a classic situation, right? Where you have an equilibrant kind of situation. We've done this before. Like this isn't actually really new, but it's just the wording of it in grade 12 is a little more technical with this equilibrant force idea, and you get lots of situations where this comes up, right? So it's kind of classified as a specific thing to watch for. So onlookers, might say, "Oh, you need to tighten the rope. There's too much slack. It's sagging." Are they right? So should we tighten the clothesline? Should we tighten the rope across the Niagara Falls or the one over Yosemite? That's the official pronunciation now, I think, right, in the States. Yosemite or something like that. But anyways, should we tighten this so that it don't have that slack? Well, the answer is no. The cable sag is necessary. Otherwise, you wouldn't have any upward component of these forces, right? They have to have an upwards component. Each one, if you're looking at this, has a sideways component, right? So call this F2, I guess, and this is F2x and F2y. And call this F1. We have F1x and F1y. And so if you look at those two y components, right? F2y and F1y, and I slide those over, they add up to, of course, the same as the addition of the two of them, right? Roughly, anyways, get the idea. All right, so yeah, you can't tighten that rope that much, right? So, if a clothesline's tightened too much, it'll break when laundry's put on it. The tension force would be extremely large value if you don't have some angles upwards. And this is literally an ask me how I know situation, because I tightened up a clothesline too much one time earlier in my life, and the cable snapped when some wet towels or a load of laundry got put on it. And as soon as it happened, I was like, oh my gosh, like I immediately thought of the physics of it, right? I should have thought of it while I was setting it up, but I got it nice and tight, try and do a good job, right? And laughed at myself as soon as it broke. I'm like, oh yeah, okay, I know exactly what happened. Way too much tension in that line to try to provide that upwards force if you don't have an angle available that it can go to. Okay, so the kind of situation this sets us up for is this, where you have equilibrium situations. You're looking for that equilibrant force, and so you have this example here of a classic kind of store sign design. It's not hard to find Google images of a design like this. So you have an object hanging, and you've got these supports and you want to know the forces in them, right? What kind of material you need to withstand the force. You look at the engineering specs for different diameters of aluminum or metal or rods and beams and so on. And depending on what you're supporting, you choose the right material, right? So the free body diagram for this, we have obviously that 30 newtons. So Fg equals the 30 newtons. And then we've got a force along this and a force along this, right? Where this is the 35. Now, I don't super like the idea of committing to values here. So I'm just going to basically show, well, there's a tension force in here, F1, let's say. Sometimes I do FT1 and FT2, but I mean, it's just complicated. So force 1 and it's a tension force. You don't need a T really to know that it's a tension in that system, right? And there's one here, FT1, or force F1 and F2, right? So I'm just going to throw those on there for now. And you might already be kind of looking at it and saying, okay, well, are these right or are they not, right? We can adjust those later though, okay? So let's just point out sizes of F1 and F2. The free body diagrams are good for helping visualize all the forces. So it's good to draw them at the start, but don't know what the sizes of the forces necessarily. That's what you're trying to figure out, right? And so I kind of think of it as like, you got a rough sketch of the free body diagram, come back and adjust it to make it nice, make it the way it needs to be. Okay. So if I had my F1, let's make this one a different size on purpose here, so we can come back and see what's wrong with it. Okay. I need to make sure it's definitely wrong, and it wasn't super wrong before. F2 is a little bit wrong, if you can see why. Okay. All right, so we're looking at the x acceleration and the y accelerations, and using that as a guide to figure this all out. So if we have 0 acceleration in the x direction, by the way, this is hopefully, right, if the thing's actually in static equilibrium, and it's, we shouldn't have any accelerations in any direction, right? So we have, that's what leads us to this analysis, right? So F net in the x direction equals the x component of force number 1 and the x component of force number 2. And so we can do the math for that. May as well go ahead and do that right now. I guess we know this is 0 by the definition we're starting with, right? And then if we look back at our free body diagram, we can see that the x component of F1 is, well, it's all x, right? So we can just say F1 itself, right? So, yeah, F1 in there, and then F2, we're just going to look at and say, okay, well, F2 would be a cosine of 35, right? So F2 would be, F2x, sorry, would be cosine 35. So it's going to be F2 cosine of 35. And technically, if you really want to be, clear on things, that's the absolute value, and that comes up shortly in later in the lesson. So I will include it, but it's generally just the size of, we just say, right? I'm pretty loose about, easy going, let's say, about, picky details like that. Just watch for that. You might have a teacher at some point that, looks for all these vector signs and absolute values and so on. I think it clouds the success in the physics concepts if you do that. So not my preference. Yeah, so that's that. And then in the y direction, again, same thing, F net in the y direction is definitely going to be 0. And so we'll do that. Might want to just highlight, we have this, and that's why we have this, right? Just kind of an efficient way of doing this instead of writing 2 separate equations and then combining them. But yeah, in the y direction, we have the F2y, we have the force of gravity, and in F1y, you look at F1, it's sideways. It's supposed to be sideways, so it better not have a force that way. Basically, that would be like a torque, which we'd have to look at later. It'd be like you're trying to twist this rod here, bend it up or down, right? Down, obviously, in this case, right? So hopefully we don't have any of that happening. So ideally, you want this to not exist at all. right? Right? So you set it up like that on purpose and look at what the tensions are needed for this stuff, right? So F2y would be a vertical component, right? So F2y would be here, opposite that 35 degrees. So we're going to do F2, absolute value of it, times sine of the 35. And then we have the gravity is going to go in as the down value. And I didn't put it on here, but the usual assumption of positives and so on, right? Typically probably like that. Maybe I'd put the positive to the left this time because of the direction of that force, but let's go with it as standard issue here. But that gravity force clearly is down of 30 newtons, right? So we're going to put this in as a negative 30. All right. So what does that give us as a result here? Hang on one second, I just have to pause. All right, sorry about that. I'm back. All right, so looking at this, what's our next step? We've got in the x direction, we have an F1 and an F2. How much we can do with that single equation with two unknowns, right? In the y direction, we only have one unknown, right? So we can solve for this thing. Right, solve for the size of F2, right? So let's do that. We're going to add 30 to both sides. Gives us, what, 30 equals absolute value of the size of F2 and sine of 35. And so then we just need to divide both sides by sine 35. You could write as a decimal at this point if you wanted, but I mean, a little more efficient, maybe easier just to write sine 35. And we just do the math when we get to it, right? So the size of F2 is what? 30 divided by sine 35. So do 35 sine of that, the way this calculator works. Then we need to do 30 divided by that answer. I think if I do memory plus, then I can do 30 divided by memory recall. That way I'm keeping lots of decimals like an engineer would and getting an answer that we round at the end, right? So if we've had everything measured to 3 significant digits, let's say, we're going to keep 52.3. Okay, so this is 53.2. I never leave room for the units there. Oh well. So 52.3 newtons is F2. So if we go back to the diagram, we look at the F2 value, it's going to be 53.2. Well, if you're looking at this one's 30, you can tell like, okay, that's going to have to be longer. Remember I said F2 was wrong, right? We're going to have it bigger than the 30 down, right? And then the next thing we're going to do as a check and a look at this thing, and that would be like, okay, well that y component, would be the same as FG, right? So I guess we already that's how we determined this, right? So like that's what we did to make this happen, right? And that looks better now that it's bigger and matches, right? That's our adjustment on our free body diagram to show that everything makes sense and fix it, I guess, right? And so now that 52.3 can go in as F2, right? So this is going to go in as the 52.3. So 52.3 in as the absolute value of F2, the cosine of 35, the F1, and 0, right? So we've got, that's an add there. Oh, yeah, so we're just calculate things out, subtract from both sides and so on, right? So basically, let's just say subtract that stuff from both sides for speed and efficiency here. Here we go. So cos of 35, hear that, and cosine of 35 equals 35 cos. So we get that, and that needs to multiply on to 52.3. I forget whether I have I should have stored that 52.3, all those decimals, and then I could have used that, but I mean, not worth redoing calculations at this point for that. We get that number, and of course we subtract that from both sides, and we're getting a negative 42.8, right? So we're getting negative 42.84, so 42.8 newtons. Okay. What's the negative telling us in this context? That F1, that force in the F1, saying it's negative. In other words, it's not in the positive direction, right? So it's to the left. And so we're looking for a value of 42 point, whatever it was here, 42.8. So 42.8 is, a fair bit bigger, obviously, than the diagram I made. And so what you're going to see, I'm just looking at the numbers here, and I'm trying to get how this works for being the opposite way. So this, obviously I need to make that a lot bigger, right? 42.8, business and that. I'm just trying to think about the idea of it balancing out in the x direction with the F2. So I think I need to put the x component of F2 in as a negative in this question. I made a mistake. So this right here, because there's an absolute value and so on, that's the same as having put a number in, right? So with that being the same as a number put in, when we put in gravity, for example, right, this is a number put in. And so it's a negative, meaning, right, down. What needed to be here in this case then? Well, in this case, we needed to have a negative in for F2 x component because it's to the left, right? So the negative F2 x component, this should have been in as a negative value. Redo that. We're going to squeeze a bracket in here, have a negative sign, and so on. And again, that negative is meaning to the left. All right, so then that means this is actually a subtract overall here, right? Let me just delete that out of there and get this in properly here, where we're saying, okay, this positive and a negative combines to be a negative, and then we're adding it to both sides instead. So adding it to both sides instead, and ending up with a positive 42.8. And so now we're looking at the positive 42.8 and saying, oh, that thing's actually to the right. Okay, so now we're looking at a positive there and saying, oh, that's to the right. Which, if you look at the free body diagram, it would sort of have to be, wouldn't it? Because up here it would sort of have to be to the right because we'd have the tension. I'm gonna have to redo my label. It's upside down and backwards. But yeah, that tension force is like this. It's pushing out, right? And that balances, if you notice, that balances the F2x, right? So F2x balancing with F1. So now we have an equilibrium situation that actually, you can see everything balancing out. You've got the upwards component of F2 balancing with gravity. You've got the side-to-side component of F2 balancing with the outward force on that rod that comes out straight from the wall. Oof. All right. So yeah, that when you're putting the absolute values, that's why I put the absolute values in there. But I just forgot that that's the same as putting a number in. So you have to watch for that. Okay, my little mistake maybe draws more attention to it, so maybe it's a good thing. Wasn't on purpose, but could be a good teaching strategy, right? So yeah, that's something to watch for there for sure. Here's another example. Just a weirder looking version. The solutions are on the next page. All there is just more angles involved, right? So I'm going to leave that for you to go through. I have some numbers there to look here, then there, and so on for going through it, but I'll leave that for you. And then the one I want to have time to spend on here is this one. Okay, so you've got equal height poles. We've got something that's suspended by these two cables. So something to watch for, like I've been saying, is when you make your free body diagram, like you got to be careful about the sizes of the forces, and so don't let someone drew if you're given a free body diagram and the arrows were a certain size, you can't trust that what they drew, let's say. And of course, you want to draw the correct one, but you might go back and adjust, like I've shown, right? I'm going to come back to this hint afterwards. This hint's the hopefully obvious one. Be like, well, we have X and Y, no accelerations, right? That's the idea of the static situation. So this is where you would say it's suspended. It's saying it's suspended, and basically, i.e., it's not moving. And so we have a static equilibrium, EQ for short. And so we have, acceleration equals 0, which means acceleration in the x direction equals 0, and acceleration in the y direction equals 0. Okay? So there's a lot of understanding there to get us on the right track, right? And so let's do it. We've got the acceleration in the x direction, acceleration in the y direction, and so on, right? So acceleration in the x direction is 0, and acceleration in the y direction is 0, our normal stuff. And so F net in the x direction is, what do we have in this case for the x direction forces? We've got, let's call this F1. If we use this as our free body diagram, we've got an F1. I'm not worrying about sizes here, just drawing it for now, and an F2. And we'll adjust sizes later on, right? But we're going to have obviously an F1x, right? So F1x. You can see that it's going to be what? Absolute value of F1 cosine of 30. In here, F2 is going to be the absolute value of, F2x, sorry. F2x is going to be the absolute value of F2 times the cosine of 40. Right? That part. There we go. So x direction wise, we're ready to go. We've got really an F1x. That's still a vector at that point, right? And an F2x, still vectors at that point. So we're not putting in a subtract of those. We're just adding up those forces. When you switch to this one being the absolute value of F1 times the cosine of 30, that's why that absolute value sign, I probably shouldn't ignore it normally in grade 11 actually to get ready for this, but it's a kind of one of those nitpicky things that you don't want to confuse people with. But so we've got that guy there. This one right here is very clearly to the left, right? And so let's just expand my little bracket actually. It'll let me. Oh, perfect. I can just do the bracket then. There we go. So expand that bracket and put that minus sign in there on purpose, right? And saying, okay, that thing's to the left. That's why we put it in like that. But because it's like a number, right? It's like putting in the gravity value or something. This one's to the right, so it goes absolute value of F2, and it's going to be the cosine of 40. I was prepared for this absolute value idea for this example. And when I was prepping this lesson, I didn't notice that I actually needed to talk about it in the first one. So on the fly, made the fix, but it happens, right? So we've got that for the x direction stuff. And, right now we're looking at that. We have these two unknowns, F1 and F2, right? Let's go to the y direction here. So in the last example, we're able to solve directly because in one of our equations, we had only one variable. Let's see what happens this time. So in the y direction stuff, we've got obviously an F, a force of gravity, I should say, just like an Fg. And we have an F1 y component and an F2 y component. So let's put some numbers in here. We've got the 0, as usual. I don't know if it's necessary or not, but we could, if we wanted to, try and keep these lined up or so. It's a little thicker this time. Anyways, we could show like acceleration 0, so net force is 0. Same idea, right? Just for emphasis for the lesson, you don't need to circle it on your page or your work or anything, but so we got 0 equals, and we got the force of gravity. Well, the force of gravity was given that it was a 2 kilogram mass, right? This time, instead of given number of newtons, we're going to say like Fg equals mg. So it's going to be the 2.0 times the 9.8. And then the f1y is going to be, they're both up, right? So plus the absolute value of f1 times what? The y components of things, right? f1 was the one that had the 30-degree angle. So f1, let's put it in here to be complete. f1 y component. Move that over in a bit, but absolute value of f1 sine of 30. All right, so f1 y component. Oh, you bugger. All right, good enough. And then over here, we have an f2 y component. It's going to be absolute value of f2 times the sine of 40. All right, let me just fix that a little bit nicer. Here. There we go. Oh, got a piece of the equal sign. Put it over here instead. There we go. Perfectionism. All right, looks a little better. And so we've got the absolute value of f1, and I've lost my train of thought here on the f1 sine 30. And then absolute value of f2 sine of the other angle, which is 40. Right? So we've got that. And so at this point, we're looking at this and we're like, oh, I can't solve for f1 or f2 here because I've got 2 there as well. So this is where you might find yourself stuck as a student at this stage trying to figure things out, right? How do we get around this? How do we fix this situation? I like my rearrangement here while I'm talking, so I'm just gonna put it back. So the thing to recognize here, right? Press pause, give it a whirl, whatever, is to notice that you have 2 equations. You've got this equation and you've got this equation, right? So we've got 2 equations. Hopefully you see where this is going, right? 2 equations. And in those equations, you've got 2 unknowns, right? Unknown number 1 and unknown number 2. Unknown number 1 and unknown number 2. So 2 equations and 2 unknowns, which means you're going to do, it's a linear system, right? And so you're going to do substitution or elimination. A math step to solve things, right? So I think people tend to like elimination in math class, but substitution tends to kind of work better in physics because they're not lined up, obviously, right? So you could do elimination though. You could just get rid of this number from the side and then maybe lined up for elimination. But I think in most cases, substitution's a little bit more of the scientific way of going about it. So that's what I'll do. So let's solve for f1. Let's take equation number 1, and we're going to solve for f1. Oops, S-O-L-E. Solve for f1. So we're solving for f1. Yeah, let's just say solve for f1 like that. That's the value of it, I guess, right? So solve for f1. And so we're going to take that equation as it was and work with it. So we've got our negative f1 cos theta cos of 30 plus absolute value of f2 cos of 40. And just to be nice and clear here, for solving for f1, we are going to subtract this from both sides. So subtract this stuff from both sides. A little bit lazy here, but I think it's clear enough, right? So we end up with the negative absolute value of f1 cos theta 30 equals the negative of absolute value of f2. I just need to squeeze that in or move this over. Let's move it over a little. Got a separate piece. Cos of 40. Right? And so now you can tell we got 2 negatives, so we can just cancel those out by multiplying or dividing both sides by negative, and we can divide out that cos 30. Divide out our cos 30. Those are all just numbers at this point, right? Pretty much the cos 30 and cos 40 anyways, but let's just leave it like that because there's a little extra stuff that I can show, some connection between curriculums along the way here. So this is an absolute value of F2 cos of 40 over cos of 30. And again, you could evaluate cos of 40 and cos of 30 and get numbers if you wanted, but there's a benefit to me not doing that right now that I'll describe shortly. Right, so there's equation, number 1b or equation number 3 or whatever you want to think of it as. So now we take that result for F1 and we plug it into the other equation. I think I have just enough room to show that here. Right, we're going to take this thing and we're going to substitute it in for F1 right there. Right, substitution. So let's do it. We've got maybe some room here to do that. Let me just rearrange my arrow a little bit. Make room for that. And so let's go for it here. We've got this equation plugged in. So we got 0 equals, and we have the 19.6. So I just noticed gravity was down. I don't know if you saw this a while ago and are screaming at the screen, looking for a fix, but that's a negative 9.8, right? Because it's down. So let's just make a note of that, right? This guy here is, i.e. it's down. And just like we had before, i.e. was to the left, right? So luckily I've caught that, negative 19.6. And yeah, there we go. So plus we have F1 now, right? So F1 is going to be put in as absolute value of F2, cos 40 over cos 30. That's F1. So sine 30 in there, and then absolute value of F2, sine of 40. Believe I have everything substituted correctly there. And the reason I left them as cos 30 and sine, cos 40 and cos 30 and so on, is partially because it's easier to write cos 40 than a whole bunch of decimals. So there's more accuracy in doing this. You don't have to worry about carrying floating point decimals. But the real reason was that I want to point out this thing and make a connection back to a math class that you have had more than likely at this point. That thing is the same as tan of 30. Right, so when you're doing calculations, you could just calculate tan of 30 instead of sine 30 over cos 30, and it just saves some number rounding along the way if you're not able to carry all the decimal points. Back in the day, you'd look up values in a book to get values of these trig ratios, and so you'd only have to look up the 1, which is a time saver as well. So it's a kind of an old trick. The purpose of the benefit of it was a little bit more older school, because now we have computers available to us all the time to give values, but there is definitely still some advantage, like I was saying, about not carrying a bunch of numbers and having to round all the time and all that. So let's get some work done here. Let's add the 19.6 to both sides. We end up with 19.6 equals, and we're going to have the absolute value of F2, and we're going to get whatever we get when we do cos of 40 times tan of 30. So here we go, 40, we're going to do cosine of it, and I'm going to store that one and in there. So I hit M plus, so that number, and then we're going to do the clear here, the tan, come on, move for me here, tan of 30, so 30, and trig function tan, and then I'm going to multiply that onto my memory recall button. Oh, that didn't work. Did it work? No, it couldn't. Tan of 30. 30 in degrees. Tan. All right. Memory clear. Memory store. There we go. Probably there now. The name of keeping a bunch of decimals, right? But 40 and cosine of it. Hope this inspires you to look at ways to use your calculator efficiently, basically. I'm trying to show this stuff to you, right? But multiply by that memory recall button. Now we're good. And so we have a number there, 0.44. So 0.44, 227. And I'm just going to show like dot, 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 meaning like I'm keeping more numbers when I do calculations. And then we also have the F2, and we have sine of 40. So sine of 40, 40 and sine. And end up with 0.642. So 642,786, and so on. Keep a bunch of numbers there if you can with your calculator and so on. And we're going to add those up. So I should have saved that 0.44227 as a memory setting. I can just add them together. But let's just do at least the approximate of this. So I've got that huge one, and we're going to add the 0.44227, and we're good to several decimal places there still. We got an absolute value of F2 is about 0.085 0. Even there, the rounding method, I'd keep that as a 0 if I was rounding. But anyways, with that special rule, right, for even rounding of the 5. Anyways, let's get this done. 0.850 dot dot dot. Keep some more. We have that. And so now I just have to divide both sides. Right? My computer to go down the page here though. So divide that number out, 1.0850 dot dot dot. And I end up with the value for F2. And it is what? 19.6 divided by that thing. So clear the memory out apparently, store a memory, and then do 19.6. Most calculators, if you just store a new number, it's just going to overwrite the other one, but divided by memory recall. Gotta learn your calculator basically, right? That's why it's so important to have a calculator you know and trust for assessments. It boggles my mind when students show up to a final exam, ask to borrow a calculator. It's like the craziest thing. 0, 6, 8, 0, 6, 3, 5, and so on. And so basically we're saying, wow, 18.0. It's the pre-made kind of a textbook question, right? It's all made to have like a nice round number in the end here. But so we have F2 being the 18.0 or 18.1 maybe. Oh, 18.1 actually. So it's not designed as nice as I thought. But 18.1 for F2. And then of course for F1, and you can go back in and figure that one out, right? F1, go and look at it. We have the 18.1 and times cos of 40 over cos of 30. Fortunately, no trick for that one that we can use right now, so I have to do it. So cos of 40, so 40 cos. I'm going to clear and save that guy in there. And then I'm going to divide, get the cos of 30 and do a division. So actually, I've done it the other way around. I can probably do it with brackets though. Divide by bracket 30 cos. Sounds like doing the right thing. Oh yeah, I think so. Equals, and then times the 18.1. Or if I had the other number stored, use more decimals and so on. But it's coming out as about 16.0. So they tried to make this number a nice number. So 16.0. Both of them they tried as best they could, right? So we're getting F1 and F2 in these things. So we go back to the three-body diagram and we see what we have for values, right? So we have the force of gravity being the 19.6. So if I put, I don't know where I want to do this right now. It's in the way here. Let's just do it on here, I guess. But we got a force of gravity of like 19.6. Right? Newtons, and then F2 and F1 here. F1 and F2 ended up being, F1 was 16 and 18, so 16 on the left. So 16 on the left. So I'm going to be smaller than the 19, so that's not actually bad. And then the other one was the 18, so almost the same size. So bigger than the other one. Let's. Oh, I'm still writing here. Let's make this a little bigger. That's the 8. That's the 19. That the 19, and then the F1's the 16, and this one needs to be bigger than the F1 because it's 18. I just want to sort of show the end result here. You look at things. Now, roughly speaking, I didn't like do a scale diagram or anything, but if you're looking at those components now, the actual sizes, we've got components this way that are canceling out. So we've got a component this way and a component this way that are canceling out. And then we have a component here and a component here that if I can add those guys together, I can drag them. I'll just move. Oh, they're all grouped on me. Let me just do a new one. So here we go. There. And separate one over here. I have to get the smartboard to make them separate by having a little delay there. There we go. This guy, the F2y component and the F1y component, what we're wanting to see there, of course, is the same size as the gravity, right? So that's my F2y actual result adjusted, and my F1y with the sizes of the forces adjusted to match what we got as our results, right? So that is the skill we need for that. So that makes sense. And yeah, so questions like that for you. This one's just straight, add them up, get the equilibrant force, whatever, right? And then we have like one of those kind of three-dimensional things to think about. Clothesline one, pretty exactly like we did in class. So hopefully that makes sense. I just wanted you to do the one here where there's like three forces. So this by the way, I think would force you to have to use trigonometry. Otherwise you have to do sine law, cosine law twice. But the AB there for practice if you want. But I'm only looking for submissions of the ones that are stated there in the typed version of things. All right. So all for now. Don't be afraid to ask for help in the post help area, and talk to you later.